Let me do the recap on what we learned in the chapter 1. Do you remember what we learned in chapter 1? Do you even remember the title? It's called Property of the Gases. Remember that? Right? So they do this one and then go to van der Waals gas, and there is a compressibility factor, which is a volume that you're measuring it, and volume that you're supposed to have, which is not a volume, it's just a volume. This is a P, RT, MIT. All right, they couldn't. Anyway, you learn about how to describe this, the gas that you learned before, and this one essentially has two properties: as no interaction, right? No volume, no occupied volume. So this one is corrected by A and is corrected by B in the van der Waals gas. And we start to learn how to describe this property of the gas. Even like they're talking about speed distributions of the gases and different kinds of averages and so on. This is actually kinetic theory of the gases, momentum transfer to understand the pressures and so on. And this is not actually macroscopic thermodynamics. This is what we call the statistical thermodynamics. But they kind of put it in a way to give up the sort of the meaning of the molecules. So once you, this is a lot of loaded topics. In addition to that, there's a lot of topics, the critical temperatures, right? Remember that, the boil temperature, we are in the technical exam. So it comes down to the fact that gases have an interactions and the Joule-Thomson experiment, and this is all related to do this. But this one is actually later that they want to talk about. Chapter 2, chapter 3. You know what chapter 2 was? First law, right? Chapter 3 was second law, even third law. And the first law is essentially delta U is U plus W. The second law of thermodynamics is essentially I don't think there's an easier way to put it in. It's just invention of a concept of entropy has happened from the Carnot cycle. And to me, the most important one is this equation. So this is understanding how Gibbs free energy is changing with the volume and the entropy as a proportional constant. So you can manipulate changing the G by changing temperature and changing the pressure. And all of a sudden that this one has a meaning of changing the G, changing the temperature, keeping the pressure constant, S. And then this is molar, this is molar. And this is how we understand the first equation. And this is what gives rise to chapter 4. And time versus your Gibbs molar energy. And this is a solid, this is a gas, and this is a liquid. Remember this, right? And so that now I can see that this is a solid, lowest energy, this is a liquid, this is a gas. So that's why we always see that at higher temperature, we always see gas. At lower temperature, we always see the solid. And we can have a pretty much very easier way to prove that. And this diagram has carried on more in chapter 5. Chapter 5 is a lot. It is what is called the mixtures. And among all this is actually d mu. So for A, the chemical potential in the mixtures, and this is nothing but when it's solution, your liquid chemical potential, solvent chemical potential is getting lower. And by doing so, you have a boiling point elevation, and this is a freezing point depressions, and this can be actually chemically and mathematically can be drawn. So this is a chemical potential equation for when you have an A and B mixtures, and A is your majority, which is a solvent. From this equation, we also developed this Bantoff osmotic pressure, and that's a Bantoff equation. And this is how he got the first Nobel Prize. If you look at his citation, he gave thermodynamics, chemical dynamics, and the understanding about osmotic pressure, and he got this first citation. And not only that, you boiling point elevation, freezing point depressions. This is all do that. And then finally we got to the chapter 6, which is delta G is delta G RT ln Q, and the delta GR is 0, and then therefore at equilibrium Q and Q becomes the K value, and so therefore delta RG naught is minus RT. So what I was really trying to really take it from here is this is a molar Gibbs free energy. Once you know the Gibbs free energy, you can really lead into the describing the mixture system, also trying to relate that into the equilibrium constant. And this is all related to at the one single snapshot. Okay. And then finally, the D ln K dt is minus RT squared. HR on this. I think this is okay. I think this is. I forgot the Bantoff equation, that whether the sign is plus or not. We'll find out. Okay. Yeah, that's right. There's no plus. This is just. So this is another one, another Bantoff equation about equilibrium constant. Okay. So this is really the first segment is going all the way, and it's essentially wanted to describe about the equilibrium constant. You need to develop this concept K, you need a G concept, and then the G is coming from the entropy, and entropy has to be derived from the scratch, and then this we need a Carnot cycle. And the invention of S. Right? S is being heat reversible over temperature. If you define this, and this is we can have a new function called entropy. That is same as can be translated into the Gibbs free energy. So this is really trying to teach you about the universal understanding framework that you guys can work on the system. And then we have jump onto the chapter 17, which is kinetics, which is totally different subjects. And this one is, I guess, the activation energy, the rate constant, and how to relate to those rate constants to understand the reaction mechanism, and this is all involved.